Okay, so just a couple more little things about work. One is this equation, I didn't really tell you the full story. This equation, W equals F delta D cos theta, it's really W equals F as a vector dot delta D. This equation is actually the first equation that you're seeing where we're multiplying two vectors together. All of the other equations that you have, we were multiplying a vector and a scalar. So F equals MA. M is the scalar, A is the vector. Delta D is equal to VI delta T. VI is the vector, delta T is the scalar. Plus 1/2 A delta T squared. A is the vector, T squared is the scalar. What other equation? Momentum is equal to mass times velocity. M is the mass is the vector, velocity is the scalar, or excuse me, other way around. Mass is the scalar, velocity is the vector. So this is the first time we're actually multiplying two vectors. And in physics, there are two different ways we can multiply vectors. This one is called dot multiplying, dot multiplication. And I'm sure you're thinking you use this dot, and math teachers use this dot all the time to just mean multiplying. But it really means something specific. It means a certain way of multiplying vectors together. And so, but instead of, like, what we define this to be then is multiply by the magnitude, the size of the two vectors, times the cosine of the angle between them. And so that's where the cosine comes from. So we'll never write it this way. We'll always write it as F delta D cos theta. But it comes from a specific type of multiplying vectors. When you take Science 12-2 next year, we'll talk about the different ways to multiply vectors. This particular way, when you dot multiply two vectors, what you get out is always, 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 always a scalar. And so that means you do not need to worry about a direction on work. Okay, so there's no such thing as you doing 80 joules east. It's just you've done 80 joules of work. It's like trying to put a direction on like 40 seconds west. It doesn't make any sense. So work is a scalar. Now, as I said a few minutes ago, though, it could work out to be positive and it could work out to be negative. Okay, and if that happens, if you get a positive and a negative work, and it was what I was saying right at the end of the video, right? So F delta D cos theta. W equals, sorry, my hand's making it go blurry. If you get positive work as a result of this, and so positive work will be when the F and the delta D are going in the same direction. Right? So your angle will be somewhere between 0 and 90. F and delta D in same direction, or at least a component of the F is. Okay, and what that means is you're increasing the energy of the object. So imagine me raising a book, okay? So imagine me standing in front of the classroom and I'm taking a textbook and I'm lifting it up. Right? So I'm putting a force upward on it and the textbook is moving up. So now I'm holding the textbook some height above the floor. It now has more energy than it did. How do I know that? Because if I was holding it at the desk level and I dropped the textbook, it would hit the floor at some speed, right? If I dropped it from here, it would hit the floor at some speed, and we could find that speed because we'd know how high it was. VI is 0, we know A. And remember, speed is connected to kinetic energy. So when I dropped the textbook from desk height, it would have some kinetic energy. But now if I raise the textbook to the height of the top of my head and I drop it, obviously the VF is going to be bigger. It's falling a further distance. It's going to pick up more speed. So when it gets to the floor, it has increased its kinetic energy. So by me doing positive work on that book, by lifting it up, I've increased the energy that it had, and so that then when I release it, it ends up with more kinetic energy. And actually by raising something, the type of work that I'm doing, the energy that I'm increasing is actually gravitational potential, but we'll talk about that in a day or two. Okay, but positive work on an object, for now, all you need to know is positive work on an object increases the energy of the object, whereas negative work on the object decreases the energy. Negative work decreases energy. And that might be me lowering the object, right? So here's the book at the top of my head, and here's the floor. And now I'm going to lower the book down to here. Well, like, I still have to put an upward force on it, because if I don't, even though the book's going down, because if I don't put an upward force on it, then it means the book's just falling. It's free falling. But if I want to continue to hold the book in my hand and lower it, then I need to put an upward force on it. In both of these cases, when I'm raising or lowering an object, assuming constant speed, then the force I'm putting on it will be equal to Fg, right? Because if you think here's the object, Fg is acting down, F is acting up, not an Fn because it's not sitting on anything. I'm just picking it up, raising it, and lowering it. So whenever it talks about lifting an object, the force you're always going to use is going to be equal to the object's weight. Okay? But here, if you look, I'm lowering it. So now F is going one way, delta D is the other. The angle between them is going to be 180 degrees, and the cosine of that angle is going to be -1, and so I'll get negative work out. Maybe an easier example to think of is, imagine that I'm moving an object this way across the floor. So I'm moving it this way. Think about friction. Friction always opposes motion. So that if an object is moving in one direction, friction goes in the other direction. So the angle between the direction the object is moving and the force of friction will be 180. Friction always, always, always does negative work. Remember we said negative work decreases the energy, and friction always takes away energy. So friction always does negative work, okay? Because it always decreases the energy. All right, now if we were to do an example, let's say a child is pulling a wagon. Here's my box. Pulling a wagon at an angle of 30 degrees with the horizontal, with a force of 100 newtons, and the wagon moves a distance of 20 meters. How much work is done? W equals F delta D cos theta. So W equals 100 newtons times 20 meters times the cos of 30. Okay, and then you just punch this into your calculator and get 1732.1 joules. It's just that easy. If we were to do one that says you're lifting, okay, so example 2, you're going to lift a mass of 100 kilograms, a distance 50 meters. Not 50 meters, maybe 0.5 of a meter. You'd need really long arms for 50 meters. So part A, how much work have you done? So W equals F delta D cos theta. And remember a few minutes ago I said if you're lifting, then the F is just going to be equal to Fg. And so that'll be 100 kilograms times 9.81 meters per second squared, and the angle between them will be 0. And so it'll equal 981 newtons. Joules. Sorry. Because I forgot, I lost my 0.5. That's what's wrong. That was newtons. And then times 0.5 of a meter. And W is equal to 490.5. There we go, joules. Now what if you wanted to lower it back down? If you wanted to lower it back down, now your delta D is down, but your F is still up. So the only thing that changes is your cos theta, and you would get negative, and that would mean energy.